Hi, and welcome to Dr. V's AP Chemistry webcast. What I'd like to talk about today is Beer's Law, sometimes called the Beer-Lambert Law after the scientist who developed it. This is something that shows up frequently on the AP Chemistry exam, and it's definitely something that my AP Chem students and anyone listening needs to know about. What I'd like to accomplish in this webcast today is talk about the basic principles of how Beer's Law works and introduce the equation. The equation for Beer's Law does show up on the AP Chemistry reference sheets, and so you need to know how it works. And then I'd like to talk about how we use Beer's Law in the lab and introduce the idea of standard curves and how we gather this information. So the basic principle behind Beer's Law involves a colored sample. It's got to be colored because we're usually looking at visible light. And we're directing a beam of light onto that sample. We're calling that here the incident light. And we can measure the intensity of that incident light, which has a wavelength of a color corresponding to a color complementary to the color of the solution. And then we're looking at the intensity of the light that gets through the sample. We call that the transmitted light. So we have to have a detector that can measure both of these. All right, so the ratio of those two is really what's important. If the intensity of the transmitted light is very, very small compared to the intensity of the incident light, lots of that light is getting absorbed, very little is getting through. If that ratio is large, so the intensity of the transmitted light is very close to the intensity of the incident light, that would be a low absorbance situation. Now, there is actually an equation that correlates these. So absorbance is defined as the negative log of the intensity of the incident light over the intensity of the transmitted light. This equation in this form is not used on the AP Chemistry exam, but sometimes students like to see where it's coming from. I don't want you feeling like it just came out of nowhere. But this does actually explain why absorbance is always reported as just a dimensionless quantity, because it really is a ratio. So let's talk about what affects the absorbance of light as it's passing through the sample. One thing that affects the absorbance is the concentration of that colored solute. Right? So if we have a certain number of solute particles, we look at the intensity of the incident light versus the transmitted light. All right, that's fine. When we increase the concentration, what we see is that the intensity of the transmitted light goes down quite a bit. That's because there are more solute particles really in the way of the beam, and so more of the particles of light, more of the particles are there, more gets absorbed, less gets through. All right, so we really see that this is a nice linear relationship. I will mention at very high concentrations, it doesn't quite hold up. We have to have really quite high concentrations, and that's really beyond the scope of what we do in AP Chem, but I'll mention that. So it's not going to be perfectly linear if you have a very, very concentrated solution. All right. The other thing that can affect the absorbance is the path length. All right. How long a distance really does the light have to travel through when we're measuring the intensity of that transmitted light? So we can actually quantify this, right? It's a measurement. So I've indicated that with the arrow L in this diagram. All right. What we see is that as the path length increases, everything else staying the same, the absorbance increases. So really the same kind of reasoning. Although the concentration hasn't changed here, I've got more particles still in the way, in the path of that beam of light to absorb the light. And so the intensity goes down for that transmitted light. And again, we see a direct relationship between the path length and the absorbance. What we find, practically speaking, when we're doing these measurements with any kind of commercially available spectrophotometer or colorimeter or whatever you have, usually we're always using the same path length, but in principle it could change. All right, so this leads us to the equation A equals ELC. Sometimes you'll see it written A equals ABC. All right, so L is the path length. We just talked about that. All right, so we see that direct relationship. C is the concentration. It might be molarity. You could use other concentration units, although it will often be molarity. And then E is the extinction coefficient. It's really the proportionality constant here. Or sometimes it's called the molar absorptivity constant. Extinction coefficient is actually an older term for that. And it's really telling us, right, for a particular concentration unit, how much light is absorbed. All right, so we're looking for linear relationships here. All right, so how this really gets used in lab is that we're going to plot absorbance versus concentration for a series of solutions and use the graph to find the concentration of an unknown. All right, so we don't have to do a lot of math per se with this equation for the AP chemistry exam, but we need to know how it works. All right, so to set up the experiment, the first thing you're going to do is make a series of solutions with known concentrations. All right, and when you know their concentrations, we can say that they're standard solutions. So that's what we've got illustrated here. These are a series of solutions of potassium permanganate, starting with a practically colorless solution where there's little or no potassium permanganate, getting up to a pinker and pinker and pinker solution as the concentration of potassium permanganate increases. So visually, we can see right now that concentration definitely is going to affect absorbance. All right. The next thing we're going to do is put the solutions one by one into our colorimeter or spectrophotometer and measure the absorbance of each one and write that down in a little chart or a table. All right. Of course, we want to keep the wavelength the same for all of them. We keep the path length the same for all of them, so we're not introducing other variables. All right, so this is a set of data that my students recorded when we did our Beer's Law lab this year. And here's the graph that would come from that data. I just made it in Logger Pro. And I've got absorbance on the y-axis and concentration on the x-axis. And you can see just how linear that is. All right, that's exactly what we want. Ideally, of course, the y-intercept should be 0, and we should have a very linear fit. We do have a very linear fit here, although the y-intercept is not quite 0, but it's really close. And the slope of the line actually gives us that molar absorptivity or that extinction coefficient. All right. And the way we use it from here is that we're going to then, separately from setting up our standard curve, we're going to measure the absorbance of the unknown. And then once we have that value, we can either use the graph and read over and down, or substitute into the linear regression equation to find the concentration of the unknown. Usually on the AP exam, the question would be along the lines of, here's the absorbance of the unknown, tell me the concentration. The other thing that they might ask occasionally is, if a data point on your standard curve is a little above or below what you might expect, they might talk about sources of error. Typically, when you are doing your measurements, you're going to start with your least concentrated solution and move to your most concentrated solution to try and minimize contaminating the solutions with something more concentrated. That's really the gist of what you need to be able to do for Beer's Law. Have a great day, everybody.